Hi everyone, my name is Tejas Chopra. I am a senior software engineer at Netflix, and today I will be talking about improving flash storage on Android phones. I am delighted to be a part of the Storage Developers Conference 2022. The agenda for the conversation is as follows. I'll talk about myself, what I do at Netflix. Then I'll talk about the Android IO stack and some of the performance issues that exist. And we will then discuss some of the proposed solutions, such as changing the journaling mode for the database, exploring different file systems, etc. And finally, we'll discuss some of the takeaways. I'm a senior software engineer at Netflix. I help build the infrastructure that is required to run the Netflix studios on the cloud. I have experience working in companies such as Apple, Samsung, Cadence, Box. I'm a TEDx speaker. I talk on cloud computing, storage, distributed systems, and Web3. I'm also an advisor to Web3 startups such as Nillion and Dorado. Along with that, I'm an adjunct professor for software development at University of Advancing Technology in Arizona. This talk is based on the work that I've done at Samsung. When we think about the Android smartphone, there are a lot of performance issues that exist on Android. When we think about smartphones in general, we are seeing that the percentage of global traffic from smartphones has been exponentially increasing. And in fact, in 2021, we were 56% of the total traffic that is observed on the internet, as well as the usage. So if you think about social media, 80% of the browsing of social media is done using smartphones. 95% of the users access Facebook on smartphone. 86% of Twitter users use it on a mobile device, and 60% of LinkedIn usage is from mobile devices as well. However, as much as the usage has increased, there are still bottlenecks that exist in the Android ecosystem. These bottlenecks have been studied by different experts in the industry. It almost always boils down to storage. Storage I/O has been identified as the bottleneck in Android as well. Now, this picture is an old picture, as you can tell from the different applications and their images here. But what this tries to show is a brief glance at the stack in Android. So you have applications that run on top of application framework. These application frameworks are built on top of libraries and runtime, which are, again, built on top of the kernel. The kernel contains different types of device drivers for blocks, file systems, audio, video, Wi-Fi, and the kernel is wrapped around the storage that is inherent in Android systems. What we did in order to improve the performance of Android smartphones is studying the data. So we looked at common application patterns and looked at the read and the write ratios of the requests that were being made to storage. A very good example, as you can see here, loading the Angry Birds application led to a 2:1 ratio of reads versus writes. Application removal led to a 1.35:1 ratio of reads to writes. We thus studied different modes of usages in the smartphone, and we wanted to optimize for all of these use cases. So if you look at the different read-write profiles, you will see that SQLite is more than 90% of the writes that are happening on both Facebook and Twitter. Metadata journaling accounts for more than 40% of the writes. The synchronous writes are more than 70%, and they are extremely random in nature. We have more than 64% of I/O read and write for these two applications that is less than 4 kilobytes. And if we see the IRQs for eMMC, they are more than 18%. Now let us dive into how we are causing so many writes in an Android subsystem. Let us take an example of an insert in a SQLite database. SQLite is a small database library, an embedded database that has been developed and is being used in Android subsystems. An insertion of a database entry results in multiple underlying writes to the file system. So when you insert a database entry in SQLite, the first step is you create a journal, then you record the data to the journal. You put a commit mark to the journal, and then you finally insert the entry into the database and you delete the journal. So this is the basis of any journaling system. You first write entries into a journal, and then you write them into their exact location and delete the journal. But this operation of writing it into a journal and then rewriting it to its intended location results in many underlying writes to the file system. Furthermore, because Android by default comes with ext4 file system, ext4 maintains its own journaling as well. So when you have a write that is happening in ext4, you again have to repeat the process of issuing that write to a journal and then forwarding the write to its appropriate location and deleting the write from the journal. Now this leads to this journaling of journals problem. So which means that a single insert on Android results in multiple writes for SQLite, as well as whenever an fsync is called, there is an SQLite journal which is written to storage. And then we have the ext4 journal, which is both the descriptor and the metadata that is written to storage. Then we have an ext4 commit to storage. And finally, when SQLite is moved to its appropriate location, we again repeat the same steps. So in some ways, one write done by an application results in 9 writes to storage. That is what is causing the most issues in Android subsystem. We then went ahead and tried to explore different solutions for this problem. The first one was choosing the correct journaling mode. By default, Android selects the delete journaling mode that has 2 fsync calls and has 9 IOs. The journaling size, which is the metadata for the write that we've done, as well as the total IO volume, is pretty high in this default mode. Our goal is to reduce the number of IOs as well as keep a tab on the ext4 journal size as well as the IO volume. We explored different journaling modes such as delete, truncate, persist, and write-ahead logging. We concluded that the write-ahead logging journaling mode gave us the best bet when it comes to the number of fsync calls as well as the number of IOs that were performed. So it also reduced the journal size and the total IO volume. And that is why choosing this mode is giving us the best results when it comes to reducing the writes that are done to underlying storage. The next thing that we tried to optimize was for the file system. By default, we were using ext4 file system in Android, but then we looked at the different file systems and the way journaling works in these file systems. As you can see here, there are a lot of writes that are performed in different file systems, and many sectors get touched for a single write that is done. Here we've compared BTRFS, NILFS2, XFS, and F2FS. Our conclusion was that XFS and F2FS give us the best amount of performance for a given write. That is, these two file systems ensure that we write very limited number of times to the underlying storage. The third optimization that we discussed in our group was replacing fsync call with fdatasync call. So whenever you do an fsync, even if you have just touched a file and you perform an fsync, the file gets flushed to the underlying disk and storage. But with fdatasync, we actually avoid sending the file if the file is just touched but the data is not modified. So this can prevent a lot of unnecessary fsync calls that are done to underlying storage. And finally, one of the larger pieces of optimizations that we did was we evaluated the number of IOs that are done, and we saw the nature of these IOs. So a lot of the IOs were random in nature and they were smaller, less than 4 KB. So we realized that small random IO is not ideal for Flash. And therefore, we wanted to convert the small random IOs to large sequential IOs. This is typically done in log structuring file systems, and we use a layer of mapping. So we translate the logical block address of a random IO to a sequential block address that we have maintained internally. And we use a layer of mapping. The idea is that between two fdatasync calls, we collect all the IOs and we sequentialize them, thereby writing one single write to the sequential location. However, this alone doesn't solve the problem because this does not handle the problems of overwrites. In order to deal with overwrites, we have to develop a garbage collector to clean up the blocks that were overwritten. So this solution also necessitated the need for a garbage collector to be written. Getting into some more design details, we chose a segment size of 1 megabyte, and we are we rely on the idea that a log is infinite, but the disk is finite. So we need to periodically clean the older segments to recover space. We maintain a liveness count for every segment. So if there is a block that has been overwritten, we actually insert a tombstone in the original location. Over a period of time, we calculate the liveness of every segment, and the segments that have lesser than a threshold number of live blocks are rewritten. So we read them back, we create a new segment. So we compact it into newer segments, and then we write those segments out. We can, of course, auto-tune the frequency of cleaning up or down, and it depends on the different applications that run on our system. Let us now discuss some of the results and what we saw with different applications. So when we changed from fsync with fsync under different journaling modes for different file systems, we saw that by just changing the journaling mode, we were seeing a difference of more than 2.8x by choosing F2FS with write-ahead logging. In ext4 itself, just changing the journaling mode gave us a 1.1x improvement. This is measured by the number of SQLite inserts per second. And then we compared the same for fdatasync. And we saw that fdatasync compared to baseline gave us a 17% improvement in ext4 and a 126% improvement in F2FS when it came to SQLite inserts per second. Now comparing the applications themselves. So here we are looking at the different execution time of some application workload. And we are looking at both Twitter and Facebook. We see that between ext4 and F2FS, by choosing fdatasync, we have seen a 71% reduction in the execution time for the same number of operations for Twitter and around 58% reduction for Facebook. This tells us that things are much faster in F2FS if we choose the fdatasync mode of operation compared to the baseline ext4 that is there in Android. Finally, let us now dive into some of the takeaways from these experiments. Android stack, as it exists, is not optimized for Flash. We have a problem of journaling of journals that leads to write amplification, and it impacts the Flash life. So the goal that we set out with was to understand the behavior of all the elements in the stack. We narrowed it down to understanding the SQLite and ext4 behavior to make better choices. These were choosing the correct journaling mode for the writes, choosing the correct file system, replacing fsync calls with fdatasync calls, and log structuring the small random writes to get better performance. The impact of these changes was that we could see a 1.5x to a 3x improvement in operations per second, and common applications such as Twitter and Facebook are much faster using these changes. This software was deployed on more than 10 million Samsung devices, and it enabled Samsung to improve the performance of Android stack for all the users. That's my time. Thank you so much. Please feel free to reach out to me on LinkedIn, email, or Twitter. Thank you.